Okay, so welcome back, guys. I know it's been a while. I've actually not updated us on any stuff, and I really want to apologize for that sincerely. I want to apologize for that. And this is one thing about decentralization, centralization, where there is an owner, and so because of that, they can do whatever they want. Um, I mean, and I really apologize. It won't really happen again. Hopefully, it won't happen again. I will keep on updating us, and we have a goal, and we hit it actually. We hit it actually, and thank you for also tuning in to be part of us. But in today's session, what we'll be talking about is ownership. Actually, I didn't plan to show my face because well, we want to visualize extensively what ownership is, how it works precisely, like know the details about ownership in Ross language. Okay, I know ownership can be complex sometimes. It can be something that you think you know, but you don't know it, and or some people might find it difficult to grapple through it and understand what it is. And so, on my left hand here is a slide, and on my right hand side here is a drawing image. Where I'll be drawing some stuff to illustrate what we'll be doing, and also this is my VS code, and this is where I will be writing some code. But we won't do much of code writing today, but shall we write some code, okay? But we won't do much of code writing. Um, so this is what this is. This is just a simple folder structure that just the name of the folder is ownership, as that's what we are going to talk about today, and that's basically what we did. But now here, this is what we are going to focus majorly on. And so I wanted it in a way whereby you can visualize and understand it precisely, so that you won't really you have an image or something to munch on, not just something maybe you'll be talking in the air. And so because ownership is very, very crucial, it's one of the very, very important features that makes us unique. And so that's why I decided to just go this route today. And if it's actually cool, if this method is actually cool, if it makes sense to you, do it to drop a comment in the comment section, and maybe tell me how you feel, so that maybe next time I might keep on with this method, or still just be teaching tutorials like that. Though it just depends. I put myself in that situation of, if I'm a student, what's the best way to actually understand this? So that's how I'm not strict with a certain kind of pattern though. So I can just, based on as the occasion demands, I'll just flex. So today we'll be talking about ownership in Rust. And I'm so sorry if you can't see my face clearly. I didn't plan to do that. So I just wanted us to just focus on this, focus on the screen, and understand what ownership is in us. So having said that, this is our topic today. What is ownership? What comes to your mind when you talk about ownership? What do you think about what is it to you when you hear the word ownership? What comes to your mind? Now, ownership in us is a set of rules, okay, that governs how ROS programs manage memory. Okay, how ROS manages memory. So that's what ownership means. Okay, I hope that really makes sense. And also, come to think about it, all programs have to manage the way they use computers memory while running. Okay, so some languages use garbage collector, where they have the garbage collector itself have to look for memories that are no longer in use and do some cleaning and whole stuff like that. And languages like JavaScript have garbage collectors, Python have garbage collectors, and also there are some other languages where the programmer itself has to actually allocate a memory and also free the memory. And so that's where C and C++ comes into play. But in in Rust follows a different route actually altogether. Rust follows a different route altogether. And this is how Rust manages memory. Rust manages memory through system of ownership that we are going to talk about today. So with a set of rules actually, and this set of rules is rules that the compiler checks If this rule really is applied, we will execute, we will run. If it violates the rule, if any of the if any of the program violates the ownership rules, it will throw an error, it will not compile. And so it's the work of the compiler to make sure that these rules are being in check before running. So that's what makes Rust actually unique, and that's the goodness of a compiler compiling before runtime. And so moving forward, we want to talk about something very, very important, which is stacks and heap. And stacks and heap are very, very important in ownership actually. That you can't but just talk about stacks and heap in Rust programming language when talking about ownership. Okay, so we want to extensively understand what stacks are and what heaps are. And so come to think about it, what are stacks? And first of all, I want you to know that both stacks and the heap are part of the memory. Okay, and these are available for us. Rust makes it available for us at runtime. And so the moment your program is running, these are made available for us. Okay, and so there is no much um, um, difference between stack and heap as touching memory. Like they are both a part of a memory, a single memory, and so their differences is based on their structure, how they store values, how they store data. So that's their differences. That's what differentiates heap from stack, and we will try as much as possible to understand the differences in this section. Okay, and so what are stacks? Stack stores value in order it gets them and removes the values in the opposite direction or order. Now, this highlighting I did here is just for you to know the importance of what I'm talking about. Okay, and so think about stacks. Now, this comes in place when you hear about last in, first out. Okay, in stacks. Now, think about stacks as a pile of plates. Like there is a pile of plates. Let me just use this diagram. This is where this diagram comes in handy. Let me select a tool and just use this diagram and express. So now this is what stack looks like. That you have a pile of plates, a stacks of plates, or a pile of plates, and when after washing a plate, you stack it on top of each other. You don't like try to slot it in between or something like that. So this is, let's say this is a stack of plates. Okay, these are plates. Don't mind my diagram. These are stacks of plates. These are stacks of plates. These are plates on top of each other. So these plates are just on top of each other. And so this is how data are being stored in on the stack. So the first data that comes in on the stack will be at the bottom, and the last data that comes in before runtime will be at the topmost. And so if the stack wants to remove data, the stack will start from the top to remove data. Hence this word first in, last out. Okay, the stack will start from the top to start removing data. It's like after washing plates, or you want to use the plate and serve somebody, you will not start from the bottom and say, okay, let me just take the bottom one. This plate will crash down, and if it's breakable plates, they will break actually. And you not say let you start from the middle, let you just take the middle plate and from the middle and serve people. No, you just take from the top. Okay, take out from the top and serve, do whatever you want to do with it. And that's how stacks work in Rust. So in memory storage, data that are stored in stacks are stored like a heap, a pile of plates. So that's the image I want you to have in mind. They are stored as a pile of plates, and the way they are stored and the way they are removed is based on the word at the top. Okay, they are stored as pile, as stacks of plates, as the name implies, stacks. And if you want to remove, if you want to remove a data or a value from a stack, you use the word pop off from stack to remove a data or a value from the stack. As you want to remove a plate from this, you just call the pop off function and it will remove this plate. And if you want to push a data on this stack, you want to add a plate on top of this stack of plates, what you do is to add the function push to the stack to add this plate. So that's just how stacks works. I hope that makes sense. And this diagram is just something to help us illustrate what this is. Okay. And now moving forward, there are things you should note about stacks that differentiate them precisely, apart from the fact that they store that the way stacks and heap store data are different. One of the key things about stack is that their data are known. They have a fixed data size at compile time. So their data are known and their size are known. So what should come into your mind when I'm talking about known fixed size should be the primitive data types we talked about and the tuple. Tuples now will be tuples that have these primitive data types in. You know, we talked about tuples as mixed data types, actually collection of mixed data types, right? We talked about it. And now, when we talk about heap, the data stored on the heap is an unknown size at compile time, okay? And the data is not known at compile time. And also, if the data might be changed, let's say this data has the possibility of being changed, or let's say that a user, yes, a particular user, we want to store a particular data at the future in this heap. You store the data on the heap. So data, as I emphasize here on with this yellow ink, data are no size and sizes might change. So imagine that let's say that you store your name on the heap, okay, that is unknown, and you know that this name will change. You might change it, or another user might want to input their name, and maybe they want to log in. This one want to input their name, this one want to input their name. It should be stored on the heap because it's dynamic. There is possibility of change on the data. So that's the key feature of heap. That's why heap exists. Their data are their sizes are unknown, and their data might change, and so that's why they are stored on the heap. Okay, I hope that makes sense. And so what are heap? What are heap data? So when a data is imputed on the heap, this is what happens. When a data is imputed on the heap, a request is narrated of a need of a certain amount of space. Okay, the memory allocator finds an empty space in the heap and marks it as being used, and then returns a pointer, which is the address of the location. Okay, this is just basically what happens. So let me illustrate. Just imagine that you came to a restaurant, and you have a team that you guys want to just hang out, okay? And you came to the receptionist or anybody that is allocating space and tell the person that your team, we want to have a space where we want to have fun together, okay? And now what the receptionist will do, or the person you inform will do, is just to go and find a place. Maybe you guys will follow them, or you guys will not follow them. They will not He will go, or she will go and find a place for you guys. Let me now when he finds a place for you guys, this is what happens. He will now return the address of where you guys are staying. So in case there is maybe another of your team member that will come late, you might easily tell the person, this is where you guys are. Oh, are you looking for these people with 4 guys or 5 guys, or with this color of shades, or with this number of people? This is where they are. Like, the pointer is just an address to the location of where the data is being stored. I hope that makes sense. I hope that makes sense. And so this is simply what the heap looks like. So the heap looks for when a data is being stored on the heap, there is a need for a space. The space is not known. The amount of space is not known. What the compiler you want to do is to find a big space for you, an empty big space for you, so that no matter the amount of data that will be stored, because I mean, at compile time, your your data is not known. The size of your data, the size of your team is not known. We don't know whether you guys will be 50, but I'm seeing 12 now. I'm seeing 12 people, but because you guys are a team, I know that you guys will be more than 12. So what I will do is to find a space that maybe that contain 50 people. Why these 12 will be seated, I will take the address. I will just know that the information of where these people are saying, whereby if other people will be coming, I'll be directing them, pointing them to where they should stay, where the other team members are. Oh, that makes sense. That's actually illustrate what um um heaps are and how the data is stored. And now this now helps us to understand that the size are unknown and the size might change. Okay, there might be change of data, there might be change of the value. Okay, is not a known size, unlike the stack that the size is known. I mean, you know that this is the amount of size of stuff you want to store, and so that's why it's being stored on the stack. Though we still talk more on this as we move forward in this video. Now, talking about this push, you know, pushing to the stack is faster. Now, it's very fast. You know, when you want to push to the stack, it's absolutely fast than allocating to the heap. This is why. Now, first of all, allocating to the heap cannot be addressed to stacks. Okay, reason being that now pay close attention. Please pay close attention. Now, when the address is being returned, when this address is being returned, this address is being returned, the location is being returned. Now, there are a few things that comes with this address. Now, the number of space that the data contains, and the number of people at that particular time. And so because of that, this is already known. The pointer is known, but the data that is being contained can change. Because it might change, it will be stored on the heap, but the pointer to the data on the heap will be stored on the stack. Reason being that the pointer is already known. Now, remember the illustration I gave to you, team members. Now, when the waiter goes and gets them a space, if he's coming back with an information already.
We have not printed out
these people are 10 in numbers, and I provided maybe 50
and that's why
for them
showing
with
on
good
our
tables and
terminal. So what we want to do is just
there's already known information. And so this already known information will be stored on the stack.
So what I'm telling, what this line of code is saying is just simple. We want you to store any value that is inside of this that this is calling.
Okay, is being stored on the stack.
That's simply what it is.
So because this
any variable,
this pointer is already
a logic,
known.
Any outcome of that logic.
This pointer is already
known. We want it to be stored.
I know that the number of
so in our logic now is just this simple
32.
Calm down.
Okay.
This is just
and I provided a
to help you understand how functions work.
60.
But in real world,
okay, because I know
this is not it's not a logic.
Okay,
this
because this data will
kind of
change.
Example.
It will be stored on
in real world. You can see
this information
that
is already known. This information is already known. That is
hundreds of lines, 50s of lines of code.
This information on its own will be stored on
and
the
so that's where
it is
complex.
Known.
So we are just telling this to just store this.
I hope it's clear. It can be confusing.
Just store this.
I hope the diagram will help us understand
stored in this variable
talking about.
Okay. So what we just do is to print.
Moving forward.
ln.
Now I say something. I'm pushing to the stack.
Print ln
faster than
ln
allocating to the heap.
And
reason being that now,
just
if you want to push
that
data,
and just write.
If you want to push a data to the stack, this is what happens. Remember, stack have a known value, and they are just stacked on top of each other. You know, the diagram I gave us before, they are stacked on top of each other. I want to
wipe up this for hope you have subscribed, and this is our 10
illustration.
Okay, so these are 10 here have been called, and so really it doesn't really matter.
I just stop here.
Actually, how you place your function.
Now this is how the stack. This is what the stack looks like.
But the fact is that you have to follow
it's just a stack of plates on top of each other. Okay,
for
these
it
are
to
just
call
stack. These
functions.
are all stacks.
Okay, so having
Just a
explained what
stack of plate, and these stacks of
expressions
plate,
and
their sizes
statements
are
are,
known.
remember key
Okay,
notes to
it can
just
be of
take out
different
from
sizes, but their
this,
sizes are known.
from
And
expressions,
now,
and also
it
what
will be
else I want
easier
us
for
to be aware is that
data.
it
It will be
cannot really
faster
understand
to push
everything at a
another
glance
set of
or
plates on
once.
this stack,
They might can be confusing
because
at
I
sometimes,
mean,
but
what you're
try
doing is
to
just
go
to back
back
on
to
top.
these
You know
videos
where your
and
data
watch
is,
them,
and it's just
okay,
easier
for you
for you
to
to
get
take
a
this
grasp
data
of it.
and put it on top of
Okay, so now
your already
this
stacked
actually,
stuff. Then, if
okay,
you want to allocate data
is
to this,
an
the
expression,
allocator
and I
will
say that
need to
expression
go and
returns
find a
value.
space.
Okay, they
This
return
allocator
something.
will now take
Why
you guys
function,
and be
why
looking for
statement
a
does not
space,
return
an
anything.
empty
But
space
in a
on the
statement you
memory.
can find an
It might
expression
go
in it.
a journey looking for an empty space on
Okay,
the memory, and when
just
it finds an empty
understand that.
space,
Okay, that's as basic as
what will
it
happen
is,
is that
like
this
just
empty space
basic
will
something.
now be
Okay,
allocated,
I hope you
marked
guys
as used
really
for
understood
you guys.
this,
And so,
and
following
I'll try
the
as much
heap,
as
following
possible
this
in the coming
process
projects to
will
lay
be
emphasis on
slower
functions again, so
to
that we can
allocating data
actually
or
the
storing
projects that will
data
be coming
on
soon
the
will be
heap.
much more of
And
functions.
since push
Okay,
already,
so that
this
we
since
get a grasp
stacks
of what
already knows
functions
where the
are and
data
how they
should be
work
stored,
in
which is
Heap.
on
Okay,
the
so now
stake, and
let's talk
know
about
that what I
parameters.
need to do is just to take this thing
Parameters.
and put on
Parameters
top
are
of it.
arguments in
I mean, I
Rust.
know where I'm going actually, but
Parameters
on the heap doesn't know where the
and
allocator doesn't know where what the allocator is doing is just,
arguments
I need a space.
in
Let me find a
Rust.
space for this man. Let me find a
Okay,
space for
so
these people for them to store their value. That's what the allocator is doing.
parameters
So
and
it might
arguments
go
in
the
Rust
way
work together
around,
when
just
calling a
looking for an
function.
empty big
Okay,
space. And so
and
that's why
imagine you're in a
allocating,
restaurant and you order a
pushing
meal.
data to the
Okay,
stack is faster
and so
than
let's say that
allocating to the heap.
the
Okay.
menu
And now,
represents a function.
accessing
The menu that
data
was given
on
to you
the heap
represents a
is
function,
also slow
and it lists different
than
meals
accessing
you
data
can
on the stack.
order
I mean,
and
when you
those
call the
amazing
push,
stuff.
you just know that
Okay, the meal
you know where your
option
data have been stored
are
already,
the
right? You know where your
parameters.
data have been stored on the stack.
That's
It's
list
just
of
stacked on
meal
top of
that
each other,
can be
and you just
choose
know
are the
that when the
parameters.
push is being called, when the pop off button is being called, that's to access the data. What you just need to do is just take the one at the top. Because strictly you cannot take from the middle, right? You cannot take from the bottom. You just take the one at the top, and it's very fast on the stack. Just take one of the plates here. Okay, just take one of the plates here and just do whatever you want to do with it. I'm sorry for my bad drawing. Just take one of the plates here and do what you want to do with it. While on the heap, this is what happens on the heap. The data is slow. Reason being that now the remember that the pointer is stored on the stack, right? And now the pointer will be pointing people back to the heap. Now, when you want to access data on the heap, that's the content of the pointer on the heap. When you want to access it, this is what will happen. Now you now have to go from the pointer. You now give you an address of where this is being stored. Remember where this data is being stored, and data that is being stored on the heap is not organized actually. And so Mr. A might be asking for an order. Mr. B might be asking for an order. Mr. A say, no, I don't want this order, I want another order. Like, before the data that is being stored on the heap is being accessed, this stack have already gone. Okay, so that's why accessing data on the stack is much more faster than the heap. I hope that makes sense. That makes sense. And so, moving forward, now, rules of ownership. When we talk about the rules of ownership, remember at the first definition, we said that um, the way Ross manages memory is through a system of ownership and set rules. And so the compiler will check if these rules are violated. If the rules are not violated, what the compiler will do is just to run. But if the rules are violated, it will not really run. So these are the rules we are talking about. And so these rules, what I want you to do is just have it at the back of your mind as you proceed. You don't really need to have it off heart, but it's a very important part of you. But as you proceed in Rush, you not really need to stress yourself on this, because you are getting used to what these rules are. Okay, so the first rule say that values has an owner. Okay, each value has an owner. So there can when we are talking about each value has an owner, what do we mean? So let me go back to our code and see if I can write something So we say that each value has an owner. So this is what we are excuse me. So let me just put this our fn here, our normal fn. Let me close this. Oops, sorry. So I'll just do fn. I think this is too big for me. fn fn then this mm, I need to close this copilot. Okay, so when we say that each value has an owner, Ross, this is what we mean. We are saying that let's say you say let's s equal um string from, don't worry, I'm giving a little bit example, block forge. Now this is it. Now this is an owner. This owns this value. Okay, this is a variable, and this variable owns this value. And so this is what we mean when we say that each value has an owner. So and the second rule say that there can only be one owner at a time. So meaning that there can be two owners at a time. But don't worry, we still digest and explain what these rules are as we move forward. So you see, just have it at the back of your mind, and we really talk about it extensively in this tutorial. Now, when the third rule say that when an owner goes out of scope, the value is being dropped. We still talk about it. And so these are the three basic rules of Ross. Okay. Now, we want to start from scope. Okay, let's just talk about scope a little bit and what scope are. So a scope is a range within a program of which an item is valid. Okay. Now let me illustrate what I'm saying here. So let me open this. So let's say, let me just see now, this s equal hello. And so this, remember our definition, we said that a scope is a range within a program where of which an item remains valid. Okay, and so this is a range from here to here, is a range within our program. And so this is the item between our range in our program. And so provided that this thing remains here and functions here, it is valid. But whenever this variable, this owner, is the owner, whenever this owner goes out of scope, the value is being dropped. So out of scope is somewhere here. Okay, the value will be dropped automatically. And so let's go back and still talk about something important. Now, the important things to note about scope. Okay, now when scope, when s, that's the variable we talked about, comes into a scope, it is valid. And so this is the s here, this s is valid here. Okay, and another important thing to note is that it remains valid until it goes out of scope. So provided that this value is in the scope, it remains valid. So let's say for some reasons you decide to call this function somewhere here and do print ln. I want to call it here. This already will be dropped automatically in Rust. We still talk about it extensively as we progress. But this is just what we are saying. The major two things you have to note is that provided that this is in each scope, it is valid, and it remains valid until this variable goes out of this scope. And we say that scope is a range within a excuse me, is a range within a program of which an item remains valid, right? So bear this in mind as you see progress. So another thing we want to talk about is string types, okay? And this should remind you of something that we've talked about, data types, okay? We talked about Boolean data type, we talked about string, not string, we talked about the char data type, we talked about the floating point data type, we talked about the integer data type, right? We talked about those data types, right? And now we are hearing something about the string type. What exactly are we talking about when we are talking about string types? What exactly are we talking about? Now, now, data types that we talked about before, their types are known. They have a size. Now, let me just jog our memory small. And now remember that this is a string literal. Okay, this is a string literal. String literal. Now, the data types we talked about before, no, the data types we talked about before, their sizes are known. They have a fixed size. So let me use an integer for this illustration benefit to joggle our mind. So let's say that let's x. Let me just explicitly add this data type u32 equal 90. Now this has a fixed size, and the size here is saying that the range is between this box size. Remember the box size illustration I gave on this integer data type, right? So the range of this is between this box size, and so this is already stored on the stack. So data types like the boolean are we still elaborate on this later, but data types are stored in the stack, and these data types can be copied, right? You can create another instance of it, another instance of this data type, but you want to look at a data type that is being stored on the heap. Now this data type that is stored on the stack can be copied. You can make another copy of it in another scope or whatever. You can make another copy of this actually, and the compiler will be very 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 fine, right? But if you want to talk about heap, you have to make sure that the data is not copied, and also the size is not known. That's the most important thing. This size is known. So if you want to talk about a data type that the size is not known, one of our main choices is to talk about this string data type. Okay, this string type, and this type manages data allocated on the heap, and as much as is able to store an amount of text that is unknown to us at compile time. And so that's why this is a good example for us to use for this explanation of ownership, because this stores allocate data on the heap and stores data on the heap, and the size is unknown, is not known at compile time. So that's why it was a good choice for us to use this. Okay, and now let me go back to our IDE, and I'll just close this and comment out this and just put string type. So this is what I'll do. I just want to write a very basic string type to illustrate something. let s equal string dot from hello. Now this double colon here, this double colon is an operator, okay, and it allows, what this double colon does is that it allows us to namespace this particular from, okay, this particular from function from our normal basic, instead of using this string underscore from, okay, it allows us to namespace this, and it works perfectly fine. Remember we did something like this in our first project, where we said let's say age equal to string dot new, and this, I explained that this allows us, it creates an empty string on the heap. Now what this does is that it creates an empty string on the heap for us, and what this does is that it is storing a string hello on the heap for us, and this heap can change. Actually this heap can change, and so that that's the beauty of using, that's the beauty of storing data on the string, on the heap, because the data is unknown and we might likely change it at the end of the day. And so let's assume that we want to actually change, we want to change this data type, just mess around with it. S dot push underscore string, and okay, and I will really ask us a very important question now, and I hope you get it right actually. So print ln, okay. So question, what is missing based on our previous lectures? What do you think is missing here? You can think about it. What do you think is missing here? And is our mute. Our mute. That's what is missing here. Our mute. And oops. Adding this mute will allow us to change, or remember, by default variables are immutable, right? We talked about it before, right? By default variables are immutable. So for you to be able to change the or add value to a variable, you must actually add this mute keyword, and so that was the missing link here. And and now if you call our compiler here and tell just run this for us, it will run very very fine, and I believe you must have actually run yours. It will run very very fine, and there is no error here. You just compile fine and you're good to go. So what's the difference between string being mutated but literals cannot? Because now for this literals, string literals, actually these string literals cannot be mutated. They cannot be, their values cannot be changed. Reason being that they are being stored on the stack. Remember the definition of stack. Now this value now cannot be mutated. The value cannot be changed. Now remember our definition about stacks. Stacks have a fixed size, and so for you to change this will not work, because, but you can change this, right? You can change this, right? You can change this, because the allocator already knows, the compiler knows already that this is stored on the heap, and if it's stored on the heap, it's either that the value is unknown or it might change in the future, right? So that's why, that's the difference between this and this. what in simple word is how they are being stored. So assuming that this is being stored on the heap, you can mutate this, right? So that's the difference between this and string literals. Okay, now let's talk about something else in this memory allocator. So when we talk about memory allocator, what really comes to our mind? Okay, now I want to strings by default, string, in order to support mutable and growable piece of text, okay, we need to allocate an amount of memory on the heap. Okay, and this memory is unknown at compile time, okay, to hold the content of our data. And so, and this now means that the memory must be requested from the memory allocator. And so the memory allocator will be the one that will request, that we really need something. Now remember our definition here about heap. Yeah, adao heap. Now remember our definition about heap here. We say that when a data is imputed in the heap, a request is generated, and so this request is from the allocator at runtime. So the memory must be requested from the now like as we've imputed this, this is what is happening. As we've imputed this is what happens. Now immediately this is being imputed, when the compiler have checked that there's no violation of the ownership rule, immediately this compiles, this need to be stored, this value here need to be stored on the heap. Okay, and so what will happen is that the memory will now request from the memory allocator at runtime. It will request from the memory allocator to give us space to put in this, so that we need space. We need space for string. So the memory allocator now we have to now go and be looking for space. Actually, this is what happened. The memory allocator we go and be looking for space. Maybe just look for something. Our board are full. The memory allocator will now start going to look for something, look for space, looking for an empty space that will contain our hello, right? Our hello. Then after, when it finds that space, another important thing to note is that we also need a way of returning this memory to the allocator when we are done with the string. Now, is the allocator that gave us the memory space, right? Is the allocator that gave us this space that we are using to store our let me just put it right here. Let's say the memory gave us this space to store our hello. Okay, our hello. Oops. Our hello. So the memory gave us this space to store our hello, right? Now, once after declaring this, when the program starts running, the compiler or the memory allocator will request a memory space from the allocator. The memory will request, I need a space. I need a space for this hello. And when the memory allocator finds space, now we store this, right? Now we also need to find a way, right, where we can be able to return this space, this memory space, because it's not our own now. It was given to us to just store a value. We need to find a way to return this space once we are done using this string, this hello, right? When we are done using this hello, we need to find a way to return this string back to the memory allocator, so that the memory allocator will know that, okay, this, we are done with this, right? Now the first part, which is that we must request from the memory allocator a space at runtime. We must request a space. The first part, which is requesting a space from the memory allocator, is done when we call this string from. So immediately this string from is being called, and the code starts running. When it comes here, it already knows that, oh, these people are requesting for a space, right? This is what happens behind this. I'm just trying to just have an image of it. So now when this runs to this point, the memory allocator, we get a request from the memory that people need space, hello world needs space, right? Like the hello world needs space, and this hello world that needs space, this was what requested for the space. Immediately this was called, the compiler knows that there is need for space, there is need for the memory allocator to look for space for us, right? And this is what happens. The memory will now look for space for us. And the second part, where after using this space that we requested and the memory allocator gave us, after using this space, we need to return the space, the memory, to the memory allocator. We are done. Okay, now the second part, this is how it happens in other languages. Okay, languages that use garbage collectors and track and clean up the memory. Okay, this is what happens. The memory is being used and you don't need to think about how to return the memory. It's just done behind the scene for those programs or those languages that use garbage collector. Okay, but when you're talking about let's say C and C++, okay, where they have to define the memory one and also free the memory, they have to allocate to the memory and free the memory themselves. This is what is very, very difficult, for languages like that the programmer have to allocate a memory and also free the memory. It's very, very difficult in the sense that, one, if we forget that if we forget to free the space, actually we waste memory, one. And if you do it too early, if you do the memory returning space to the returning the memory to the memory allocator on time before it should happen, this is what will happen. We have an invalid variable, right? And if we do it twice, there will be a bug error. And so the process of you allocating a memory and also freeing it can box you in a place of just fixating your mind in something that Rust have actually dealt with. And so this is what happens in Rust. When this memory is when this memory we are done with it, okay, what happens is that Rust calls a drop function.
You imputed something. You wrote
at this point, which we can return the memory. Okay, we are finished. We are finished using it here. We are done using this memory here. We are done using this hello world here. Okay, because
that is actually undergoing a process. There is a function going on.
Let's see if you can call this cargo
to return something for you.
Cargo run.
Okay. Let's write some code to explain what you're talking about. Number add underscore number, and you add our parameters I.
This is it. Hello world. Okay. Just a basic hello world. Now we are done calling this memory.
Remember, parameters
are done calling this memory
a variable name,
and we are done using it here. So this is what happens. Now the
I32.
The Rust itself, okay, returns this memory. Our string use.
We are talking about return value,
and we don't need to stress about how will you return it or how we don't need to return it. Immediately the variable goes out of scope here, okay, because what happens is that we are done using this thing here. And so if Rust want to use the same variable maybe and check after this scope, it will call a drop function. And this is where the author of the string can put the code to return the memory, right? And Rust calls this drop function automatically, okay, at the closing curly bracket. And so this is what happens here. So after using this here, we are done using this. So as the program runs, it will still want to use this variable to still validate if there is any other place it was used. And so immediately it goes out of this scope, it will call the drop function immediately, because because why? We are done using this memory, right? We are done using this memory, and the memory will be returned back to the memory allocator. And so that's how ROS manages it, than giving us that headache of maybe putting it, returning it too fast or returning it twice, and all these bug. And the issue of returning a particular memory twice, or a variable twice, causes a very big bug. Okay, and I will still talk about this later in the future actually. So maybe I'll talk about it when we are done with this course. Okay, but there are three major errors that low level languages face that was dealt with. Okay, but don't worry, it's not our focus. It's really out of the scope of our learning today, but we'll still talk about it later. Okay, so now, having talked about how memory is being allocated and how strings return their allocated memory and all this stuff. Now, let's talk about a very important stuff also. Now, how do variables interact with data? Okay, how do variables interact with data? Now, what I will do is simply, I'll just control A and just wipe up this, right? And just do fn main. I just call this function. Now, now remember that multiple variables can interact with the same data in different ways in ROS actually, right? And let's look at a very basic example. Say let's x equal 5, and let y equal x. Remember, you said that multiple variables can interact with the same data at the same time. So this is data. This is data here, and this is the variable. Oh, but question, doesn't this actually violate our rule of where the ownership, there must only be one owner at a time, and each value has an owner? Yes, actually. But now, this value are stored on the stage. Ownership is actually strictly on the heap, right? Does it make sense? These are known value. These are known fixed size value, and they are stored on the stack. And because they are stored on the stack, ownership rule doesn't really affect these people. They are just on their own. So ownership rule affects the data that are stored on the heap, right? Now we can probably guess what is happening here actually. You know that this is still telling this, okay, now this data here, I want you to see have this kind of data, and let's see if it will run. Let's see if it will run. Print ln. Okay. um x y. Cargo run. So let's see if it will. Of course it ran. Now it still begs the question, but we'll still talk about it later. Okay, now this compiler is just on a very sweet level, doesn't really want to do all this stuff. And remember our definition of stacks have fixed value, and so any data that has a fixed data size is stored on the stack. And so this is one of the things you have at the back of your mind. This stack does not really violate the rule of ownership. Ownership works on the heap. Okay, I'll start as much as possible to repeat this so that we really understand what we are talking about. And they say that repetition is the mother of emphasis. I'll try as much as possible to keep repeating this as much as I can. Okay, now let's talk about heap. Okay, data that is stored in the heap, and let's see how ownership plays a role here. Okay, now let's say let s1 equal string dot from. We still use our previous example, hello, and let's say let s2 equal s1. Okay, do you think that this will work? Do you think it will work? Do you think it will work? Obviously, remember what is happening here is that these two variables are interacting with the same data, right? With the same data, right? But in this place, something there are different stuff happening here. Okay, here this is what is happening. The remember our rule of ownership that one owner at a time, and each data must have a unique owner, right? Now this means that this variable s1 is the owner. Oops. This variable s1 is the owner of this string here, right? Is the owner of this string here. And so trying to make maybe I love my brother, I love my bro, I love my brother is of my blood, and he wants to share the same he wants to share the same data with this guy here, right? As this one did, you know, what others did. I want to follow them and do the same. You know, as this let x equal to x, let x equal to 5, shared a data, was just working in love and shared the data with this, and they all shared it, and the compiler was fine. This man here decided to do the same. Actually, he decided to still work in the same love and share with his brother or twin brother and stuff like that. Now, this is what is happening. This s1 is automatically moving the ownership of this string to this person, right? This is what simply that is happening. It's not, there is no, now what is happening here is that this data is copied to this. Remember what I said, that stake value can be copied, but here it's strictly that this is moving this data directly. S1 is moving this data directly to S2. Simple. Like, we are not sharing, we can't share. The rule is very simple. It's either you're having it or I'm having it. We can't share it. Okay, that's what is happening here. And so now if you try to call S1, you really run into an error. Now let me explain something. Let me go back to our diagram and let's see if we can explain a bit something. Now this is S1. Now remember that this S1 this is a pointer. This is a pointer to the actual data that is stored in the heap. Now remember what I said before, that heap has a data already. A variable has a data already that is being stored on a heap. And what the allocator will do, we return a pointer, an address to the actual data. Remember, our function is just hello, right? Hello. Now what the compiler will do, what the allocator will do, is just to index this one after the other. Index is 0 index, right? 0 1 2 3 4 5. This is 5, but it's 0 index, right? Now it will now index this and store it on the heap for us, and returns a pointer. And this pointer comes with three things. It comes with the pointer at the address to the place, and comes with the length and the capacity. And now when you're talking about the length, you're talking about how much memory in bytes the content of the string are currently using. And so this is currently using just five memory space in byte actually. And also the capacity is the total amount of memory in byte that the string has received from the allocator. Now remember, what the allocator does is just to find a very big space for the string, right? And so the capacity might be bigger than this, can be 10, but the actual length, the actual memory that is being used by the current data is 5. It might be 10, it might be 15, depending on the allocation of of the memory allocator actually. And what determine the allocation is depending on the request that was being made by this guy. Remember the request that was being made by this guy. I hope that it's actually making sense, right? The request that was being made by this. Now remember, this is what is happening here. This is S1. S1 is the original owner of this data, right? Now S1 is the original data, is the original owner of this data. Now this is the data here, and S1 owns this hello world. Okay, I'm using a diagram to help us explain what this now. S1 owns this, and this is how S1 owns this. And now S1 wants to feel actually, he's just feeling generous. He wants to share. He wants to work in love. All this stuff, all this beautiful stuff. He now decides I want to share with my brother. I want to share with my brother, and let's just share the same way. Now, the same way. Now have this image at the back of your mind. This is what is happening in this image, right? What is happening in this image. Now this is what happens with X and Y. X and Y have the same data, and they have the same different variable, right? And they're sharing the same data. This is what is happening. But in our string, this is what S1 intended, that okay, bro, me and you, we're gonna share this simple data in the heap, right? We share it, and what will happen is that you have a copy and I'll have a copy, right? This is what we want. But this is actually what is happening now. When we assign S1 to S2, the string data is copied. This is what is happening when we assign S1 to S2. Remember when we assign this X to Y, the string data is just everything. It was copied because the size is known and it's fixed and it's stored on the stack. And I mean, it's just fast and everything can go through and we'll be fine, right? We'll be fine. And on this place, this guy wants to replicate this data that is stored on the heap, right? And the actual thing that happened here is that the string data is copied. The string data is copied is what can be copied on this end in this heap is just this data. This data here, the pointer, the length, and the capacity. And this capacity, this diagram here on the S1 is stored on the stack. Remember, I said that the pointer is already known. Now, this is the size. The size is already known. The capacity is already known, right? It's stored on the stack. Known value are stored on the stack. But the heap is not known. It can change. There can be variable. It can actually change, right? The variable can change. And now that's why it's being stored on the heap. This is returning this, and if it's returning this, you already know, okay, you guys are only 5 and I allocated maybe a capacity space of 10, but the length of you guys are just 5, and so it's known and it's being stored on the stack, right? But the actual data of the pointer is stored on the heap. Now what can be copied when we write something like this is just the data that is stored on the stack, right? The data that is stored on the stack can be copied. Pay close attention, guys. Pay close attention. The data, everything that is stored on the stack can be copied. Okay. But if you're trying to copy this, if you're trying to copy the actual data, copy the actual data from the, like, for it to look something like this, we are not sharing the same data and sharing the same thing. Ross can't run it. It's very, very expensive for us. It's quite expensive. And this is pay close attention, guys. Now, Ross, instead of copying the heap data as well, right? What it does is just to actually because this now is very, very expensive, right? What it will now do is just to carry you that want to show love, carry those value, both carry this data and the value, and just give it to S2, right? It will just copy everything and just send it to S2. And so now if you try to run this, this S1, it will drop automatically, because this is S1 is no longer existing, right? The illustration can be like you gave your key, your car key or your house key to somebody. At that point, you don't have access to your car or your house. Is that person that has the key that has access to it, right? But let's say you gave the person a spare, both of you guys can access the same thing. And so this is what's happening here, this here, and this one above, right? And let's just see if you can call this and see what will happen. S1 actually. Let's see if you can call both. Print ln. Now let me just say this as it just came to my mind now. Okay. Now the problem was when S2 and S1 goes, what is happening here is that, earlier we said that when a variable goes out of scope, ROS automatically calls a drop function, right? When a variable goes out of scope, ROS calls a drop function, right? We talked about it, and cleans up the heap memory for the variable, right? That's what happens. And but in this scenario now, this picture, let's say this happens. This is the problem. Okay, it shows that both data points are pointing to the same location. Okay, both data are pointing to the same location. This is a problem in other programming language. Both data are pointing to the same location, right? And this is a problem when S2 and S1 goes out of scope. So imagine that both of them have the same are pointing to the same location. When S2 and S1 goes out of scope, okay, they will both try to, the memory will try to free the same memory. S1 and S2 want to free the same memory, and it can cause what we known as double free error that happens in other languages. Okay, and now this is causing a very big memory issue, right? When you're trying to free memory twice, it can lead to memory corruption. Now this S2 and S1 is pointing to the same data, right? This is what is happening. So you can copy this. This is now copied to this, but they are pointing to the same data. This is not what is happening. Okay, this is not what is happening. Their data, the data stored in the heap is not copied as well. What was copied was the data stored on the stack, and both of them are pointing to the same heap memory, right? And so if both of them goes out of scope, this is what is happening, that the allocator will try to drop all of those things, and it cause a very big bug issue in other languages, right? And free memory twice can lead to memory corruption, and this can potentially lead to security vulnerabilities that happens in other languages, right? And to ensure that memory safety happens, us actually we just carry that your love stuff that you're trying to show your friend. As S1 wants to show this love to this guy, what Ross will do is just kuku carry this man, just carry your this thing and give it to this man, and we are good to go. We don't need to come and be doing all this serere that happened up here, right? No. Now this is what will happen. Now let's say we call S1. It's showing an error already, right? The compiler is showing an error. Well, let's shall call it. Let's call this function and see what happens. So now this is the error message that is showing up. Say the value will be loaded after move. So so move occurs because this one has a type string, okay, and which does not implement the copy threat. That's simply what is happening here. Now this s1 was moved to s2, the data value was moved to s2, and so this s1 is no longer existing, right? There is no value that there is not, it's not, this is no longer existing. And if we call s1, if I call s2, oops, I don't know why this is, because I really zoomed very well. If I call s2 here and save this, the compiler will be fine and all of us will be fine. And if I look at go run, it will run hello tab show, right? And so this is and this is how you understand how data interacts in this place. Now remember, a small recap here is that this is stored on the heap. When these two lovebirds, okay, are trying to replicate what this man did here, okay, what these two lovebirds did here, they forget that their value are being stored on the heap, not on the stack. Okay, these data value are stored on the stack, but this is stored, the value here is stored on the heap, and the pointer to the value is stored on the stack. Okay, I hope that is not confusing. Now this is what happens when s2 is trying to now, when s1 is trying to share the value or the data stored on the heap, it caused an issue, a memory issue called double freeing. Okay, and it leads to vulnerability. As I said before, it's part of the errors that we find, right? And I will explicitly make a video on that and just explain what it is totally, right? But for now, let's focus on ownership and understand what it is. Now this is basically what happens on ownership, right? This is what happens on ownership, and this is how interaction happens. Remember, interaction happens using ownership, on ownership and in ownership. And so now this guy here is now the owner of this value. He's no longer s1 that owns this value, right? But if we had if you've had the terms before, shallow copy and deep copy, okay, while working with other languages, and if you've not heard about it before, it's fine. Shallow copy and deep copy. Now, as touching this did a copy. What happened here that this value was copied to this y, but in Stack, both deep and shallow copy is not really their business, because you don't have anything deep to copy. You just have to copy value and go your way, right? In in values that are stored in heap, you can have what we call deep copying, and that can allow us to copy the value, or that would copy the data stored in the heap to another variable. So that means that we can replicate what this is doing here in here, right? And so we can enforce it directly. But Rust does not give us that privilege today. But like privilege to do it, we must explicitly add it. So let the compiler and Rust know that, okay, we are doing it in our right mind. It's not just that we are following the flow, like we are following the flow here in this data type, right? Now, this is what happens. Okay, we do want a deeply copy in the heap data, so there should be a deep copy in the in the heap data of the string, not just the stack data. Because what happened here is that the stack data was copied and they were both pointing at the same data, and Rust doesn't like it. So you have to do is just to move this value to this second one, so that this one will rest, right? This s1 will rest. Just move the value to s2 and s1 will rest, right? And now but if you do a deep copy, right, both of them can share the same value in Rust, and Rust will be fine. Okay, and don't worry, we will discuss more about this syntax stuff in the coming video. We still discuss about it, but now this is what happens. This is what you want to do if you want to copy for any reason you want to still copy the value on the heap, so that there will be two variables that can interact with the same data, right, as their brother is doing up there. Okay, so this is as the x and y did, right? This is what you do. Just do this dot clone. Okay, this dot clone will make it possible for us to be able to clone this data. And so this is what happened. This is what is happening. And now if you add this dot clone, this is what is happening here. So s1 and s2 is now sharing the same data on the stack and the same data on the heap, right? They're interacting with the same variable, and so this has been copying to this have its own variable. Now they are not pointing at the same location, right? Just that they are storing the same kind of value but in different locations, right? I hope that makes sense. And now this is what is happening here. And if I call this method, it should run perfectly well. S1 and okay, let me just add something. This is S1 equal so that we know that, because all of them are just having this hello world. S2 equal, then just put S1 and S2, and you notice that the compiler is very very fine. That is not panicking or doing any stuff. The compiler is fine actually. And so this is what you do and wait for it to run. So now it's just saying that S1 has the same value with S2. The same way the X and Y are having the same value, this is the same way the clone is having the same value here. So it makes sense, right? It makes sense. Now let's really talk about this stake data copy issue that happened up there, right? Let's talk about it. Let's talk about it, guys. Now remember here, we want to just talk about this a little bit. This code seems to contradict what we interacted with, and I've explained it that the reason is that the types such as integers that have a known size at compile time are stored entirely on the stack. That's just the reason. The way they are stored, that's the reason. And so the likes of what's it called? Integers, booleans, character type, tuples, and these tuples now will be tuples that have only this kind of data types, maybe integer, boolean stored in it, right? Yeah, that's when tuples are in this category, and floating points also are also in this category, right? I hope it makes sense. And so excuse me. And so this what I was talking about. Now let's talk about something else in ownership also. So ownership. Let's talk about function ownership. Functions and ownership. So the mechanics of passing a value to a function are similar when those we are assigning a value to a variable, right? The same way you are assigning a value to a variable here. You are assigning a value to a variable here. Okay, that's the same way it works in function. Okay, passing a variable to a function, remove or copy it depending on the kind of variable you're passing to it, right? That's just, it simply how function works. So let's say that you did just say let s string, right, string dot from. What is just happening is that I have to clean up this. Let me just wipe away this or let me just comment them out. Yeah, it's better like that. I just did control shift and the forward slash to comment them out. So I just store this value here. I just say hello. So remember what I said before. This is what is happening. This already, when this compiler is running, this seeing this string from, we cause a request to be sent that there is a need for a memory, right? Pay close attention. Now let's call another function. Let's say fn text ownership. Text ownership some underscore string. Let's do string and oops, I don't know why I keep string. It's it shouldn't be inside here. Now do print ln, then just close this. Remember what you said before, that in function you can move or copy variables, right? Depending on the kind of variable or the kind of value stored, right? Now use some underscore string. So the function we talked about before, this is just a parameter that you are being calling here, and this is the data type. The data type is string, right? The data type is string. Have it at the back of your mind. So let's still do another one for copy. Let's say fn make copy some integer I32. The value is known, right? It has a fixed size, right? It has a fixed size. So you just do print ln. Sorry, I have a little bit of running nose as kata in Nigeria here. That's what you used to call it, kata. I'm getting better though. Some integer, right? So now these two values have been called, right? The parameters are there, and what we need to do is to call these functions inside the main function, right? Or inside there, and just add an argument to it, right? Remember what we talked about in about functions. I hope you can remember. And if you don't watch the video, do it to go and watch it. Actually, it's one of a kind. So now this is what is happening. Let's call this function take ownership of s, right? Take ownership of take ownership of s. Let x equal 5. Make underscore copy x. Now we say that depending on the kind of value that is being stored, right? Now the kind of value that is being stored here is stored on the stack, because the variable is known, while the one here is stored on the heap, right? Remember what is happening here now, that this string have already moved. The value of this have already moved from this person to this person to this function here. So this function is now the sole owner of this string variable, because this have already moved from the original owner, which is s, to this person here. That's simply what is happening. And let's talk about something briefly and we just call it a day. I'll just love this. Let's talk about returning values and scope. So let me just clean up this also. And as I said before, I don't my GitHub is not for you to go and copy code. As much as possible, try to code along with me and learn along. And I mean, this is just basic tutorial. Just try to learn along if you really want to learn. On those issue of trying to copy, clone GitHub and stuff like that, is for me it's just laziness. I don't buy the idea actually. Some people can do it, but for me it's laziness. It brings that room for lazy people. So use underscore. Let's say, let's first of all declare this here. Let's say fn gives underscore ownership, and this will return a string, right? Remember, let me just write it here. Let me just be plain on what you're talking about. We're talking about return return values. Return values and scope. Now this, now what you talk about return value when you're talking about functions, right? This, you're just telling the compiler that what this will be returning will be a string data type that is stored on the heap. That's just simply what you're telling the compiler at this point. So let's say let some string equal string from yours. Just call some string, right? Then now just go here and just finish up our declaring give give ownership ownership. Oops. Let's just declare one or two stuff here. Let's s2 equal string from hello, and let's s3 equals text underscore and underscore give. Just want to, we still create this function. We've not created this here. I'll give back s2. We still create this function. Let's fn. Oof. Let me this. That was a simple one. Fn, and this we have a parameter string. Why are you giving me this? And it will return string string. And we just declare this a string, right? And declare this parameter here. So this is what is happening here. A brief one. So I think I'll just lower this more. Yeah, I hope you guys can still see it so that you get a broader view. This is what is happening here. So s gives ownership Okay, what happens here is that, remember, what this string will be returning will be is a string. So this ownership, this gives ownership function gives its ownership to this variable here, this variable s1, and so this variable owns this value that is stored here, and this value that was stored here is yours, right? Yours, right? Just a random name, yours. You can change it to your name or anything. So now, this is what happening. F1 gives ownership to gives its ownership to S1 here, right? And S1 now is now the rightful owner of this function. And so if you try to call this function, and this function will be dropped, there won't be any value. Like, let's say you're trying to call this function here, right? It will be dropped because one, the value and everything have been transferred to someone else that is not the function itself, and this is what is happening here. And so S2, where is the second ownership? So text and give. Now this is what is happening here. Remember, this is also returning a string, right? This is valid. This parameter was returned here is valid provided it's inside of this scope, right? Now this is what is happening here. S2, there was a string created here, S2, and what happened was that S2 gave out its ownership, right? S2 gave out its ownership to S3. So now S3 is the sole owner of this. S2 gave out this was S2 gave out its ownership to take and give back. But take and give back gave out its ownership to S3. And so S3 is now the rightful owner of this value. So it was just moving from one person to another. But now if you are trying to call this S2, the value must have been dropped. Let's try and see if we call it and see what will happen. Let's say print ln.
Okay, and just see how what will happen. Let's say S2. The compiler should throw an error because now this is already not. Let's just see what will happen. So now it's still throwing this same error that the parameter takes ownership of the value, right? There is this have already taken ownership of the value. This parameter have already taken ownership of the value, right? And now move to. Okay, I hope that makes sense. That's how ownership works, and I took this time to explain this so that you'll be able to understand it, at least for a start. You'll be able to understand it and try as much as possible to go back to this video and try to rewatch it and rewatch it again and jot down stuff. There was a lot that was said already, and in my next session, look out for my next session this week. Still be dropping another video on referencing. Okay, referencing will be a better reference and borrowing, where we talk about how to borrow without taking an ownership. You can borrow this function without actually owning it, right? That's where referencing and borrowing comes into place, without taking an ownership. I don't want to own you, but I just want to borrow you for a while. After doing what I want to use it and do, I'll still return it back. So that's what we'll be talking about next. Look out for that and pay attention to it. If you have any question, drop it in the comment section, and do the way to subscribe and share actually as much as possible to your friends. And I'll see you in my next video.